Hi everyone, welcome to our presentation on SAFR. We will present our small, accurate, and fast ReID models for edge and mobile devices. My name is Abhijit Suprem. I'm a PhD student from Georgia Tech. We will first talk about the vehicle ReID problem, our motivation for this work, and challenges in designing for the edge. We will then cover SAFR components and our SAFR model. We'll also examine each of the SAFR components in detail, and finally we'll provide experimental results. Vehicle ReID is the task of identifying and tracking the same vehicle from multiple cameras. Associated with this are a few subtasks. We need to be able to identify a vehicle from multiple angles and camera resolutions. We also need to differentiate between similar looking vehicles. Here, for example, we see 4 vehicle identities that need to be tracked across cameras that capture different parts of the vehicle. These challenges are defined as the intra-class similarity problem and the intra-class variability problem. The intra-class similarity problem is where vehicles from different identities or classes look similar. This might be because they have similar colors or are the same make and model. The intra-class variability problem is where vehicles from the same class, which means vehicles with the same identity or license plate, look very different. This can be due to different camera angles. This is an example of intra-class similarity and intra-class variability. The dashed boxes represent the ground truth identities. We have 3, blue, brown, and red. Each of the vehicles' detected identity is from a simple feature extractor. The 2 vehicles in blue box are each assigned to different identities. This is an example of intra-class variability. The first detected identity is matched to the second vehicle in the ground truth brown identity because they are captured from a side view. This is an example of intra-class similarity. To handle interclass similarity and ensure vehicles from different angles are matched, even though they're the same identity, we would need to follow vehicles' features from different locations. This way, we avoid matching on global features that may be common across multiple vehicles. In this case, we would match on the reflective mirror and the roof rack. To handle intraclass variability, where some local features are hidden, we still need to keep track of global features. This way, we can combine both to get the best possible matching result. In this case, we would match on the light brown color and the fact that the vehicles are SUVs, in addition to the reflected mirrors. Vehicle ReID is useful for a variety of traffic monitoring operations, but it needs to be fast for real-time monitoring and tracking. Current approaches are multi-model approaches with many subnetworks. This approach is useful for offline analysis, but it's infeasible for real-time tracking. Leveraging cloud solutions are expensive because multiple model copies need to be used to keep track of all vehicles across all cameras. So, designing for the edge requires a variety of techniques. Models need to be efficient to run quickly on the edge. While real-time performance at 30 to 50 FPS would be difficult, with video sampling one could get real-time performance by using every 8th frame, for example. So we built SAFR models under these guides to be small, accurate, and fast. Our SAFR models therefore are tiny compared to related work and require less computations, making them ideal for low compute environments such as edge or mobile devices. In addition to being small and fast, SAFR is designed to handle intraclass similarity and intraclass variability. SAFR accomplishes these with 3 components. First, we have a modular design with a replaceable backbone. We use ResNet and ShuffleNet with dense layers removed for our experiments. We also use global and local attention to handle intra-class variability and intra-class similarity. Finally, we employ a bag of tricks to improve efficiency and accuracy. This is the overall SAFR architecture. Input images are fed through global attention. Then they pass through the ResNet blocks with local attention. After combining global and local features, we extract more features with the rest of the ResNet blocks. During training, we employ triplet loss and softmax loss. We employ ResNet and ShuffleNet as backbone feature extractors for different experiments. We use only the convolutional layers for feature extraction and remove the dense layers, since they add significant memory and computation overhead to the models. After training, we prune the lowest weight filters and retrain to further reduce model size. Since models are less effective after pruning, and since we already use small feature extractors, we need to improve the feature quality that has been extracted. We do this with global and local attention. Local attention improves local feature extraction for ReID. However, using only local extraction can drive the model to only look at local features. So we employ a global attention module to allow the model to keep the global features. The global attention module is inserted after the first ResNet or ShuffleNet block. We use 2 con filters to extract attention weights. with a leaky ReLU to retain the negative weights. The impact of global attention is clear. Before attention in this image, many features are lost due to lower activations. After global attention, which is second to the two below rows, allows more activations and thus more features into the rest of the network. This in turn increases activation density and reduces sparsity. High sparsity is useful in the deeper layers and when classes are different. For re-ID, the classes are very visually similar since we are only comparing vehicles, so we need higher activation density in the beginning to pass through more features for re-ID. Simultaneously, we use local attention to extract local features. This is accomplished with a dense block attention module. First, we extract channel attention and then spatial attention. We combine this with global features with a learned channel mask. Local attention improves local feature extraction. For example, we show that it can extract license plates and headlights across cameras for the same vehicle. Together, global and local attention also impact sparsity. Global attention, as we mentioned, increases density in the early layers. The addition of local attention ensures sparsity decreases faster the deeper in the backbone we go. This is because we still want high sparsity in deeper layers to improve computation. Accordingly, we show the per layer activation density. The baseline has low density, which means high sparsity throughout. Global attention, which is the blue line, starts with the highest density and decreases as we increase depth. Local attention ensures that the density increases more quickly with respect to depth, so combining global and local attention together yields the best possible result. Finally, we employ a bag of tricks to further improve accuracy. These tricks include multiple loss functions, layer normalization, and data augmentation. We use a combination of loss functions during training. Specifically, we use triplet and softmax loss together. Triplet loss ensures vehicles of the same identity are clustered together, while vehicles of different identities are pushed further apart in the embedding space. Softmax loss is used to further increase discriminative ability. The triplet loss takes an anchor, a positive, and a negative to compute the embeddings. It makes sure that the anchor is closer to the positive and further away from the negative, which is a different class. And it ensures this through a margin constraint, which is alpha in the equation. The margin constraint is the minimum distance between the anchor and the negative versus the anchor and the positive. Softmax loss, on the other hand, is a standard loss used for classification. The softmax loss operates on a dense layer that takes all of the features and then tries to identify which vehicle it would match to. Because the test and training sets are different, the softmax loss and the associated dense layer are only used during training. During testing, we don't need it. Batch normalization is common in neural networks to improve training. However, batch normalization requires constant batch size. Now, in this case, we are using triplet loss, where the batch size changes during training. This is because we're using batch hard mining with triplet loss. Triplet loss requires 3 images for each input, and the images are an anchor, a positive, and a negative, where the anchor and the positive are from the same class and the negative is from a different class. Now, often if you're using random batch selection, the negative is a completely dissimilar image of the anchor and positive, which means the model doesn't really learn much because it's very easy to differentiate between vehicles of the same class and vehicles of different classes. So, under triplet loss with batched hard mining, we only select the most difficult example in each batch. This means in many batches, most of the images are unneeded or are discarded because they're too easy, and we only use a fraction of the batch to train. In this case, the batch size therefore changes during training. So we employ layer normalization, which is independent of the batch size. Group normalization is another type of normalization that is independent, but we don't use it because group normalization assigns different weights to different channels. Under layer normalization, all channels have the exact same weight. Finally, we add 2 data augmentation techniques. Random erasing augmentation has been shown to work in person re-ID. With it, we remove a random rectangular part of an image and replace it with a pixel average of the rest of the image. This way, the model has to make do without some important components and has to learn about local features from other parts of the image. We also test with a warm-up learning rate, where we ramp up the learning rate in the first 10 epochs to improve convergence and learning, because that way the model doesn't get to a steady state too quickly. Accordingly, we design a variety of SAFR models for the continuum of cloud to edge. SAFR Large uses a Resin 50 backbone and attention at all blocks. It is designed as a cloud model for more difficult ReID queries. SAFR Medium and SAFR Small are stepping stones to edge devices, each with a smaller ResNet backbone and limited local attention. By limited, we mean the local attention is applied only to the first ResNet block and not to the rest of the blocks. Finally, SAFR Micro is designed for edge-type or mobile devices. It uses a ShuffleNet backbone, which is built for Raspberry Pi, with some layers removed for efficiency. We evaluate our models on the following vehicle ReID datasets. Very 776, which has 776 vehicle identities, 200 of them for testing. VRIC, which has 5,000 vehicle identities. Images in VRIC are of lower quality and higher noise. We also use VeryWhile, which has 3,000 images in the test set, and Vehicle ID, which has over 25,000 identities in the training set, and some of them are used for the 30% are used for the test set. Evaluations are conducted with the map metric and rank 1 metric. Under map metric, we measure the ranking quality, where the top k retrievals for a query vehicle are checked against a ground truth. Rank 1 checks what percentage of the first retrieved image matches what the query vehicle identity. In combination, they provide a good idea of how well the model functions. We compare SAFR Large to current states of the art. SAFR Large outperforms all current approaches across all datasets, except for Vehicle ID, where the parts model approach performs slightly better. On Very 776, SAFR Large has a 15% higher MAP metric and 5% higher rank 1 compared to the parts model. We also test our models against a baseline that uses ResNet 50 but no attention modules or bag of tricks. Each of our models, including SAFR Micro for edge and mobile devices, performs better than the baseline since they have attention modules and bag of tricks to improve accuracy. The models are also small. SAFR Micro has only 1.5 million parameters. SAFR Large, in contrast, is the largest model since it has multiple attention models and is based on a ResNet 50 backbone plus attention modules at each of the blocks. The SAFR Medium and SAFR Small are correspondingly smaller because they use ResNet 34 and ResNet 18 with only one attention module. Accordingly, each of our models performs better than the current approaches. So the baseline performs better than the state of the art, primarily because we use ResNet 50, and it has been shown that ResNet 50 alone is very good at ReID. When we add attention modules and our bag of tricks, we further improve performance. In addition, our models are also significantly smaller than the current approaches. Now, in a previous slide, we had shown our models alone. Here we compare our models against some existing approaches like OIFE, which we mentioned had 20 subnetworks, RAM, which is a region-aware model that had 3 subnetworks, and MTML, which is a multitask mutual learning method that had 4 submodels. So in conclusion, we've presented here the SAFR family of models. SAFR models are small, accurate, and fast models for ReID. They can be deployed on the continuum of cloud to edge. In literature, ShuffleNet, which we use for the SAFR Micro model, achieves 2 to 5 FPS on Raspberry Pi. We, in this case, further improve it by removing additional unnecessary layers in the end, and so it can have slightly higher FPS on a Raspberry Pi. All of our models achieve high accuracy and are significantly smaller than the current state of the art. For example, SAFR Micro, which has an MAP of 75, which is slightly better than the baseline of 74, has only 1.5 million parameters. SAFR Large has many more parameters because it is designed for the cloud. Thank you very much for your time. We would like to acknowledge our sponsors for their support.